Okay. Section 9.3, inferences for correlation and regression. Again, you can take a look at your focus points, pause it and take down the notes if you are a note taker. All right, learn more, earn more. We have probably all heard this platitude. The question is whether or not there is some truth in this statement. Do college graduates have an improved chance at a better income? Is there a trend in the general population to support the learn more, earn more statement? Consider the following variables: X equal to the percentage of the population 25 or older with at least 4 years of college, and Y equal to the percentage growth in per capita income over the past 7 years. A random sample of 6 communities in Ohio gave the following information, shown in Table 910. We can compute the sample correlation coefficient R and the least squares line Y hat using the data from Table 910. However, R is only a sample correlation coefficient and Y hat is only a sample-based least squared lines. What if we used all possible data points X and Y from all US cities, not just 6 towns in Ohio? If we accomplish this seemingly impossible task, we could have a population of X and Y pairs. From this population of X and Y pairs, we could, in theory, compute the population correlation coefficient, which we call rho, pronounced like rho, and is a Greek letter. We could also compute the least squared line for the entire population, which we denote as Y equal to alpha plus beta X using more Greek letters. Go ahead and pause the video here so you can write down the differences between the sample statistics and the population parameter. Again, remember for the exam and the like, I am not that big of a picky person that I will give you whatever you put down. But the program might have an issue, so you may want to go ahead and write it down. And also, if you take a higher stats class or something of the next college era arena that you're in, you may be required to know the differences. So go ahead and pause the video or just write over top of my rambling for that. All right, testing the correlation coefficient. The first topic we want to study is the statistical significance of the sample correlation coefficient R. To do this, we construct a statistical test of rho, the population correlation coefficient. Go ahead and pause the video so you can write down your procedure. All right. Let's return to our data from Ohio regarding the percentage of the population with at least 4 years of college and the percentage of growth in per capita income. We'll develop a test for the population correlation coefficient rho. First, we compute the sample correlation coefficient R using a calculator statistical software, or if you prefer, by hand. Please be aware that you do not have to do anything by hand if you have figured out how to use the calculator or any other statistical software. If doing it by hand and with the calculator is easiest to you, then by all means, please do so. R is roughly 0.887. We now test the population correlation coefficient rho. Remember that X represents percentage college graduates and Y represents percentage salary increases in a general population. We suspect that the population correlation is positive, rho greater than 0. Let's use a 1% level of significance. So H sub 0, or your general hypothesis, is going to be rho equal to 0, no linear correlation. Your alternate hypothesis is going to be rho greater than 0, positive linear correlation. Convert the sample test statistic R equal to 0.887 to T using N equal to 6 with a degrees of freedom equal to N minus 2, so 6 minus 2 would be 4. And then here is your T formula. So again, you just have to plug everything in and you get T equal to 3.84. The p-value for the sample statistic T equal to 3.84 is shown in figure 915. Since we have a right-tailed test, we use the one-tail area in the student's t-distribution, table 6 of appendix 2. Remember, I believe I have told you more than once that it would be highly behoove you to print that table out. From table 911, we see that we have 0.005 is less than p-value, which is less than 0.010. Here you go. Here's all your information. So you're looking between 3.747 and 4.604 for one-tailed. So there's your information. Since the interval containing the p-value is less than the level of significance of alpha equal to 0.01, we reject the null hypothesis and conclude that the population correlation coefficient between X and Y is positive. Technology gives a p-value of about 0.0092. Caution, although we have shown that X and Y are positively correlated, we have not shown that an increase in education causes an increase in earnings. Standard error of estimate. Sometimes a scattergram clearly indicates the existence of a linear relationship between X and Y, but it can happen that the points are widely scattered about the least squared lines. We need a method besides just looking for measuring the spread of a set of points about the least squared line. There are three common methods of measuring the spread. One method uses the standard error of estimate. The others use the coefficient of correlation and the coefficient of determination. For the standard error of estimate, we use a measure of spread that is in some ways like the standard deviation of measurement of a single variable. Let y hat equal to a plus bx be the predicted value of y from the least squared line. Then y minus y hat is the difference between the y variable of the data point xy shown on the scattergram figure 916 and the y hat value of the point on the least squared line with the same x value. I'll give you a few minutes to draw that diagram out if you are someone who takes notes. Okay. The quantity y minus y bar is known as the residual. To avoid the difficulty of having some positive and some negative values, we square the quantity y minus y hat. Then we sum the squares and for technical reasons divide this sum by n minus 2. Finally, we take the square root to obtain the standard error of the estimate denoted by S sub e. You can take a moment to write down your formula if you like. Go ahead and pause the video as well to write down your procedure. And if I haven't said it before, I'm pretty sure I have. I would definitely write these procedures on something that you can use for the exam because I think they are very handy to have. June and Jim are partners in the chemistry lab. Their assignment is to determine how much copper sulfate will dissolve in water at 10, 20, 30, 40, 50, and 60 and 70 degrees Celsius. Their lab results are shown in the table 912, where Y is the weight in grams of copper sulfate that would dissolve in 100 grams of water at X degrees Celsius. Sketch a scattergram. Find the equation of the least squares line and compute the error. Okay, so here is your line of best fit and your scattergram. Here's your 5-column table. And you're just going to plug things in to find everything else that you need. Okay, so there's your equation. Again, make sure you're pausing the video as you need to. All right, notice that the line passes through the point 40 and 30.4. Another point on the line can be found by using x equal to 15 in the equation of the line y hat equal to 10.14 plus 0.51x. When we use 15 in place of x, we obtain y hat equal to 17.8. The point 15 and 17.8 is another point we use to graph the least squared line in figure 917. The standard error of the estimate is computed using the computational formula. Again, they figured everything out and plugged it in. Note, this formula is very sensitive to rounded values of A and B. So if you're not getting exactly what the WebAssign platform is getting, it's probably a rounding error. All right, confidence intervals for Y. The least squares line gives us a predicted value y hat for a specified x value. However, we used sample data to get the equation of the line. The line derived from the population of all data pairs is likely to have a slightly different slope, which we designate by the symbol beta for population slope, and a slightly different y-intercept, which we designate by the symbol alpha for population intercept. In addition, there is some random error epsilon, so that the true y value is y equal to alpha plus beta x plus epsilon. Because of the random variable epsilon, for each x value, there is a corresponding distribution of y values. The methods of linear regression were developed so that the distribution of y values for a given x is centered on the population regression line. You guys can pause this and read this to yourselves or write it down. I'm not reading anymore. All right. Go ahead and pause the video to write down your procedure. Okay, let's look at this example. Using the data of table 913 for an example, or from example 7, find a 95% confidence interval for the amount of copper sulfate that will dissolve in 100 grams of water at 45 degrees Celsius. If you remember, they went by tens, so 45 would not be a given value. First, we need to find the y for x equal to 45 degrees Celsius. We use the equation, and we get about 33. 95% confidence interval for y is then 33 minus the error less than y less than 33 plus the error, where e is equal to that nice long equation. From example 7, we have n equal to 7. The sigma, or the summation of x, equal to 280, summation of x squared to 14,000, x equals 40, and the error is equal to 2.35. Using n minus 2, we have 7 minus 2, which is 5 degrees of freedom. We find from table 6 of appendix 2 that t of 95% confidence is 2.571. You plug everything in, and you get about 6.5. Therefore, a 95% confidence interval for y is 26.5, less than or equal to y, less than or equal to 39.5. This means that we are 95% sure that the interval between 26.5 grams and 39.5 grams is one that contains the predicted amount of copper sulfate that will dissolve in 100 grams of water at 45 degrees Celsius. The interval is fairly wide, but would decrease with more sample data. Inferences about the slope beta. Recall that y hat equal to a plus bx is the sample base least squares line, while y equal to alpha plus beta x is the population base least squared line computed in theory from the population of all xy data pairs. In many real-world applications, the slope beta is very important because beta measures the rate at which y changes per unit change in the x. Our next topic is develop statistical tests and confidence intervals for beta. Anyone who has taken your basic level algebra will have already known how important slope is. Again, go ahead and pause for your procedure. And the second part of your procedure. All right. Plate tectonics and the spread of the ocean floor are very important topics in modern studies of earthquakes and earth science in general. A random sample of islands in the Indian Ocean gave the following information. X equals age of a volcanic island in the Indian Ocean, units in 10 to the 6th years. Y equals the distance of the island from the center of Mid-Oceanic Ridge, units in 100 kilometers. There you can see the data points given to you in the table. Starting from raw data values, x, y, the first step is simple but tedious. In short, you may verify if you wish that the summation of x is equal to 415, summation of y is equal to 128, summation of x squared is equal to 30,203, y squared is equal to 2,558.5, summation of the product is 8,133, x bar is equal to 51.875, and y bar is equal to 16. Now, if it were any other PowerPoint, if this was a PowerPoint that I made, I would say go ahead and just believe me, or I would work it out with you. But you may want to double check them, at least with some of them. I'm not saying that I did it or that I have an issue with it, but we have caught multiple mistakes on these PowerPoints, so there is that. The next step is to compute B, A, and S sub E. Using a calculator, statistical software, or the formulas, we get B roughly equal to 0.1721, A roughly equal to 7.072. And since N equals to 8, we get the error equaling to about 6.50. Use an alpha of 5% level of significance to test the claim that beta is positive. So we're using alpha equal of 0.05, your null hypothesis beta equal to 0, your alternate hypothesis beta greater than 0, and the sample test statistic is T. Go ahead and write the rest of that down. We use the student's t distribution, table 6 of appendix 2, to find an interval containing the p-value. The test is a one-tailed test. Technology gives a p-value roughly equal to 0.0244. Since the value containing the p-value is less than 0.05, we reject the null hypothesis and conclude that at the 5% level of significance, the slope is positive. Here's all your supporting data. All right, D, find a 75% confidence interval for beta. For C equal to 0.75, D equal to 6, or degrees of freedom equal to 6, the critical value T sub C equal to 1.273, the margin of error for the confidence interval is, so you got to find your E first, which is roughly 0.0888. Again, make sure you're pausing and writing stuff down. I would recommend going through these before you do your homework. Using B equal to 0.17, a 75% confidence interval for beta is between 0.08 and 0.26. The interpretation means recall that the units involved are X in T to the 6 years and Y in 100 kilometers. It appears that in this part of the world, we can be 75% confident that we have an interval showing that the ocean floor is moving at a rate of between 8 millimeters and 26 millimeters per year. Computational hints for sample test statistic T used in testing rho and testing beta. In section 9.2, we saw that the values of the sample correlation coefficient R and slope B of the least squares line are related by the formula B equal to R over SY. B equal to R times SY over SX. Using this relationship and some algebra, it can be shown that for the same sample, the sample correlation coefficient R and the slope B of the least squares lines have the same sample test statistic T with degrees freedom n minus 2, where n is the number of pairs. Consequently, when doing calculations or using results from technology, we can use the following strategies. Calculations by hand, find the sample statistic T corresponding to R. The sample test statistic T corresponding to B is the same. Using computed results, most computer-based statistical packages provide the sample test statistic T corresponding to B that is the same as the one with R. I'm not going to restate some of this stuff. Okay. So that is the end of that section.